Good morning, everyone. So we are project number 11 and we are going to present the paper. So I'm going to share my screen. So myself Anurag Verma, and we have Kusoni, Manakandi, Sanjeev and Dev Nogia as our group members. Can anyone all see my screen? Okay, thank you. So, okay. So the project we have, the title is Cavity Enhanced Photon Indistinguishability at Room Temperature and Telecom Wavelengths. This was published in Nature Communication at 2024. So indistinguishable single photons within the telecom range of optical fibers play a crucial role in the long distance quantum communication. Now, while the solid state emitters have made significant progress achieving photon indistinguishability, but the thing is they are applicable at the ambient temperatures, and we want them to work at this room temperature so that we can use them in to this quantum communication and all. So this paper demonstrates a significant enhancement in photon indistinguishability at room temperature by coupling individual nanotube defects that we call NTDs with a fiber-based microcavity opening in the incoherent good cavity coupling region. So they developed a system that exhibits superior efficiency compared to the traditional one that we used before. So the ability to two indistinguishable single photons to interfere at a balanced beam splitter, resulting in their simultaneous exit through one of its output port, is fundamental to quantum photonic technologies, including quantum teleportation, quantum computing, and quantum optical metrology. Now, solid-state based sources of indistinguishable single photons have witnessed tremendous progress in the past decades. Such, for example, semiconductor quantum dots stand out as they enable the generation of pure and indistinguishable single photons when coupled to optical microcavity. Now, the main drawback that with these two techniques that we used before was that they are restricted to cryogenic temperature and wavelengths that are near infrared region. But we want to operate at ambient conditions and telecom wavelengths to facilitate long distance quantum communication. Various quantum emitters are there for emitting pure telecom band single photons at room temperature. For example, color centers in silicon carbide, gallium nitride, and the one that is discussed in this paper is this luminescent nanotube defects entities that are sp3 functionalized single wall carbon nanotubes. These allows precious control unlike the others that we have over the emission wavelengths via covalent sidewall chemistry. They are easy to integrate with gated structures, microcavity, or plasmoid cavities. All of these make entities excellent candidates for the development of source of quantum light. Now, entities, as we say common in all these previous emitters, are subject to strong dephasing at room temperatures, due to which the coherence time of the emitted photons is less than the population time, which leads to the small value of the photon indistinguishability. So, if we represent coherence time with T1, and then photon indistinguishability will be written as T2 by 2T1. Now, our main goal is to reduce this T1 and to increase this T2. So reducing T1 to enhance the photon indistinguishability via Purcell enhancement. Now these were applied to quantum states and erbium ions previously in the literature. But the above techniques were operated in the regions of coherent or incoherent band cavity coupling that relied on the cryogenic temperature, and that we don't want. So in this paper, they have demonstrated enhancement of photon indistinguishability for telecom bands, single photons from individual entities coupled to an optical microcavity, where the photon coherence time is determined by the cavity line width. And by choosing cavity with a spectrally narrow line width, we can enhance T2, and thus photon indistinguishability of the coupled NTDD cavity system will increase. And at the same time, the cavity enhance the emission via Purcell effect. Thus, we get increase in the efficiency of our system by at least a factor of 4, and with an estimated increase of photon indivisibility by 2 orders of magnitude as compared to free space entities. Their results experimentally established the rhythm of incoherent good cavity coupling as a powerful strategy for optimized source of quantum light. Now, I would like to invite Kustoni to present the method section for this paper. Will you present this?
I can share the screen.
Okay.
Yes. You have to enable me to share the screen. Enable नहीं किया. Now. Just give me a minute. So everybody can see my screen, right? Yeah. Okay. So here we are going to learn about the methods and some insight, like how the experiment will be going on and the processing will happen. So starting with the sample preparation, we'll be preparing functionalized carbon nanotubes. So first we have to get the carbon nanotubes from this, as we can see, that company, the prepared nanotubes. After that, we are going to dissolve them in the chlorosulfuric acid in this concentration. This helps in dispersing the nanotube without causing bundling. Okay. Then after that, we will be adding some functionalizing agents, that is 2-amino 5456 trifluorobenzyline sulfonate chloride, and this is prepared by these two solutions, as you can see on the screen. Okay, and with this given concentrations. After that, we are going to mix this carbon nanotubes by dropping the acid drop by drop in the nanopure water and stirring it vigorously. This will lead to the formation of entity functionalized carbon nanotubes and in the black solid form, as we know. Now, as we are preparing it with using chemicals, so there can be some excess reagents, some excess chemical maybe remain in the water, remaining in the solution. So we have to purify it. For that, we are going to filter it using the rinse multiple times. Filter it and rinse it multiple times with the nanopure water. After that, we are going to put the prepared entity in the this sodium deoxychlorate solution, and going to centrifugate it, so that for 1 hour to remove nanotube bundles. Now we are going to do the colority sorting. The entity, the thing is, the entity was sorted to obtain 8,6 colority and this nanotubes using aqueous two-phase extraction. This extraction contained, the solution contained 2% of DOC, dianeutium oxide, and with this given concentration. Now, this first step has been completed. We have prepared the sample preparation of entity functionalized carbon nanotubes. Now, after that, we have to deposit this entity on the planar mirror. So there will be two mirrors we will be using. One is planar and second is concave. The concave mirror will be come in the later part when you are going to study the setup. So first taking the planar part. So coating of entity on the planar mirror and with the spatial layer. So a macroscopic planar mirror was spin coated with this concentration 10 microliter of 3% weightage polystyrene by toluene solution. And this spin coating is performed at 2000 rpm for 1 minute, and this will give us a 150 nanometer thick polystyrene space layer. And this coated mirror was vacuum, and this coated layer will be dried for 24 hours in the room temperature. Now, same, there will be another layer deposition of entities on mirror. So 5 microliter of entity containing solution of spin coated onto the mirror at 3000 rpm for 1 minute. And by this, we will complete the deposition of entity on the planar mirror. Now, the second aspect is fiber-based activity. So our experimental setup, and the experimental setup is ultra stable fiber-based open cavity platform. The platform, like we will be using this platform, Clivery Quantum and Clivery Deform to study this. So fiber-based cavity. For the cavity structure comprised of a microscopic planar mirror with 150 nanometer thick polystyrene spatial layer and functionalized carbon nanotube entities on the top. That we have already seen how we have deposited the entities on the mirror. Then second is concave my fiber mirror of radius of curvature this, and are prepared by CO2 laser ablation. So this is the fiber mirror, concave fiber mirror. Now the second is spatial layer purpose. The purpose of why we are using spatial layer. So this is used because the 150 nanometer polystyrene layer help position the nanotubes at the antinodes of the cavity mode for the maximum interaction. As we are studying the interaction of light and matter, so we want the maximum interaction between them. So for that we are using the spatial layer purpose. So this is the purpose of spatial layer. So the next is precision control. For the precision control, we are using piezoelectric positioner. So piezoelectric positioner allow the sub nanometer precision tuning of cavity length and later scans with the three transition degree of freedom. Now the next thing is mirror coatings. Both fiber and sample mirrors had DBR coating made via ion beam splintering and designed for the high reflectivity at telecom wavelength and the minimum transmission 95.2 ppm at this wavelength, 15335.4 nanometer. Now the cavity performance. We are going to learn about the cavity performance. So this is highest frequency recorded is this 3010 with the error of 10 at the wavelength of 1468 nanometer, and this is near the E11 peak. You are going to like look at the E11 peak in the later on sections. Will be explained by my teammates. And the next is lowest accessible mode order. This equal to 4, corresponding to the mirror distance of LC equal to 2.6 micrometer. This LC and the distance will be like shown in the later section using the images. So the next we come into the photoluminescence and the photocorrelation experiment. So the first step will be excitation source. So pulse supercontinuum white light source. We are going to use this operating at 78 megahertz at the repetition rate and filtered at 2 nanometer line width. Now cavity tuning. We are going to tune the cavity. So adjusting and by modifying the mirror distance of to match E11 transition. The distance was this LC equal to 2.1 micrometer. So emission collection and filtering. So this PL is nothing but this photoluminescence. PL emitted through the planar mirror was collimated using a achromatic doublet lens. The lens is this, filtered using two long filters, Thorlabs and the Samrock. And this filtered signal was coupled into the single mode fiber for the further analysis. So this, now the detection system, this will be conducting of superconducting nanowire single photon detector. The name is this, and the photon timing recorded using TC-SPC module. The full form is with this. Now the next section contains the photo correlation and the interference experiment. So for the photon correlation and the interference experiment, we are using the second order photon correlation measured using this Henberty-Brown twist HBT setup. Okay, so used to measure the single photon parity of the emitted light. Now the next is the two photon interference Hong Kong Mandel effect via Mach gender internominator. So mechanical, this will comprise of mechanical delay stage enabled sub picosecond precision tuning of the internominator delay and polarization control achieved using fiber polarization controllers by the Thorlabs. Now the next step, the last step is data processing and uncertainty consideration. We have to also consider the uncertainty that are coming under the experiment. So for the histogram generation, detection event were integrated into 2.5 nanosecond wide time windows. Histogram displayed peaks separated by excitation pulse delays. Correlation functions calculation was done G2 by the G2 HBT function as we have discussed here. And the thing is by the normalization histogram by the average peak of n infinity. The uncertainty consideration as the main uncertainty is in peak height measurement n0 at gamma equal to 0 was under root n naught, and Gaussian error propagation was applied for the quantities derived from the measured peak heights, and the second order correlation functions at 0 time delay. Okay, the relation of G to 0 is this. The normalized second order correlation function is this. G to 0 is n naught by n1 in the brackets 1 plus minus 1 upon root n naught. Now the error estimation was this is the Dow counts and the background noise were corrected in the during the experiment, and the uncertainties in the infinity and the background were negligible compared to the domain uncertainty from n naught. So this was the some I think for the array estimation. Now for the results, I will call Mainak and Sanjeev to carry forward.
Okay, I would like to interrupt. Dev Nogia will
Uh,
introduce some like proofs in between that
oh,
we have
okay.
given this. So you can stop your screen and Dev can
Huh.
present.
Hello. Am I audible?
Yes.
So now can you share the screen?
So now we are starting the proof of regime of incoherent good entity cavity coupling. So in this regime of incoherent good cavity coupling, the condition 2g is very smaller than gamma plus gamma star plus k, and kappa is very smaller than gamma plus gamma star. Holds here g is equal to light matter coupling strength, and the gamma is population decay rate, and the gamma star is pure diffusing rate, and the kappa is cavity line width. So the line width was measured as kappa is equal to 35.4 plus minus zero point 0.1 micro electron volt. The pure diffusing rate is equal to gamma star is equal to 8 plus minus 2 milli electron volt. So for the estimation of light matter strength, we have the value of g. So g have the value of 3 lambda square c by 8 pi neta cube vc tau rad in the under root. So we have such values like lambda is equal to wavelength of light, c is equal to speed of light, vc is equal to cavity mode volume, neta is equal to refractive index, tau rad is equal to radiative lifetime. By varying tau rad between 1 to 15 nanosecond, we can see the g ranges between 17 to 64 micro electron volt. So we have some we have some final conclusions here. Since 2g is very smaller than gamma plus gamma star plus k, and the emitter decays mostly through non-radiative and dephasing processes rather than strong coherent coupling. The cavity enhances the emission but does not reach the strong coupling regime, and where quantum effects like Rabi oscillation. So the second point is regime of low Purcell enhancement, where the A point is Purcell factor and photoluminescence lifetime. So what is Purcell factor? The Purcell factor refers to the enhancement of the spontaneous emission rate of an emitter such as an atom, molecule or quantum dot when placed inside a resonant optical cavity. So we have some terms here like tau PL, which is tau PL is equal to tau Fs upon 1 plus Fp star. So where tau PL is the PL lifetime and tau Fs is the free space lifetime. Also Fp star is equal to R by gamma, where R is the emitter cavity coupling rate and the gamma is the spontaneous emission rate. So for the slow decay tau F is equal to 91 fps, and for the fast decay it is between 4.1 into 10 raised to the power minus 4 to approximate 6.2 into 10 raised to the power minus 3, and these small value indicates weak Purcell enhancement. Okay, so the next point is radiative decay enhancement. The Purcell factor Fp quantifies how much the cavity boosts the radiative decay rate. Fp is equal to 3 lambda cube Q effective upon 4 pi square neta cube Vc, where Q is the effective quality factor, lambda is the emission wavelength, neta is the refractive index, Vc is the cavity mode volume. So for the bad cavity regime, kappa is very greater than gamma, where Fp is equal to 4g square by gamma radiative into kappa. So for the effective Purcell factor, we can also write as Fp star is equal to neta q into Fp, where neta q is quantum fraction spontaneous emission contributing to useful radiation. In this system, nq is emitted contributing to useful radiation. In this system, sorry. So now we start the single photon efficiency. The single photon efficiency beta c measures the probability of an emitted photon. So we have some formulas here like IEM is equal to F into neta out into neta system into neta AM into beta C. So for the F is laser repetition rate, neta out is the probability of a photon exciting in the cavity, neta system is the setup efficiency, beta C is the free space emission efficiency. So the minimum estimated beta C is 3.9 into 10 raised to the power minus 3, while the theoretical value is 6.6 into 10 raised to the power minus 3. Cavity coupling improves single photon efficiency by at least 44 times compared to free space emission. Now, C point is cavity enhanced PL intensity. The single photon emission efficiency beta C is given by beta C is equal to kappa R by kappa R plus gamma into kappa plus R. For the pure cell regime, R is very smaller than kappa, which is simplifies to beta C is equal to Fp star upon 1 plus Fp star. PL intensity is proportional to Vc inverse, confirming the small cavity volumes and hence the light matter interaction. Thus, the cavity coupling simplifies boost photon extraction efficiency. So this was the my part. Okay.
Okay, so thank you so much. So we did three proofs that these three methods that this paper used increases the overall efficiency and photon indistinguishability. Now the main results will be discussed by Mainak and Sanjeev. So first I would like to call Mainak. Mainak, can you share your screen?
Yeah, am I audible now? Yeah. Okay. Let me share my screen first. Here comes it. Entire screen, right? Sure. Yeah. Can you see the screen? Hmm. Okay, wait. Okay, so I'm going to present the results now. Here we can see the nanotube defect is kept at room temperature with a functional group attached to it, and there is a cavity of cavity length LC, and we will use that to generate single photon sources. So, this depicts the fiber-based Fabry-Perot cavity used for studying the nanotube defects. Now, these nanotubes are deposited onto a macroscopic planar mirror with a polystyrene spatial layer, ensuring optical alignment with the intracavity field antinode. Now, a concave mirror was positioned opposite the planar mirror, forming a stable cavity structure. Now, these piezoelectric actuators provided precise control over the cavity length, and we'll later see that by varying the cavity length, we can see what results we will get. So we can control these parameters, cavity length and lateral positioning, by which we can optimize the spectral and spatial overlap between the nanotube defect and the Gaussian cavity mode. Now, the emitted photons from the system are collected through a single mode optical fiber
after transmission through the planar mirror. So this is our setup for the generation. Now, okay, so first we will plot excitation wavelength and wavelength, and we have shown the photoluminescence by the color in the left side of the graph. This illustrates the PL excitation map of an aqueous suspension of functionalized carbon nanotubes. So these nanotubes exhibit an excitation resonance at a very specific wavelength corresponding to so-called E22 transition, E22, with subsequent emission around some fixed wavelength through the E11 transition that is shown here. Now, this 1-1 transition gets redshifted to E11 star transition that is shown here, which is approximately centered between 1400 and 1500 nanometer, and this arises due to excitations localized at nanotube sidewall defects. Okay. Now the emission wavelength was fine-tuned into the telecom bands, telecom S band, by selecting a specific functionalization group. So the functionalization group is given here actually. The functionalization group it's given here. It's trifluorochlorosulfonyl aryl compound. Now we can plot wavelength with the photoluminescence. Wait, and we can show the E11 and E11 star redshifted, both redshifted and excited E11 peaks very clearly here. Now the distributed, okay, so I want to mention one point. The distributed Bragg reflector mirror coating was engineered to achieve a very narrow cavity line width at the target telecom emission wavelength. To eliminate unwanted signals, long pass optical filters were applied to block the excitation laser and emissions below 1400 nanometers, such that we can get accurate detection. Now let us analyze the effect of cavity actually. So this figure illustrates the cavity coupling, how cavity coupling influences the spectral bandwidth of the emitted photons from nanotube defects. So under ambient conditions, the spectral width of the nanotube defect emission is primarily dictated by a pure dephasing at the rate gamma. The rate is known as gamma. And the detuning that is shown here is related by that gamma, by the Pauling relation. Gamma equals 2 times, the detuning gamma equals 2 times the dephasing rate gamma. Now, experimentally, okay, but we can easily see from this graph that by using cavity coupled system, we can have better results, right? Okay, so now cavity coupling emission fixes the emission spectral density, which is factor. Now, this Purcell factor follows the following relation. It is proportional to G square, actually, where G is the light matter coupling strength. So, as G increases, the probability of photon being emitted into the cavity mode is also increases. However, in the incoherent good cavity regime, this probability remains lower than the free space quantum yield because of large spectral mismatch between the emitter's natural line width and cavity line width. Now, our aim is to maximize this G, which can lead to a substantial increase in photon emission efficiency. This enhancement significantly surpasses the efficiency obtained using spectral filtering at a bandwidth kappa or an equivalent temporal bandwidth. Okay, now these individual nanotube defects were identified by mapping the photoluminescence intensity as shown in these two graphs. The photoluminescence is plotted using the color shown here by the legend, by the color map. These maps were generated by performing a lateral raster scan of the macroscopic mirror while keeping the cavity length fixed. These two graphs, this left-hand side figure and right-hand side figure, these two correspond to two orthogonal linear polarization in the detection path. As you can see, this is parallel to the axis of the emitter and this is perpendicular to the axis of emitter. So for a given NTD1 thing, for a given nanotube defect, we can plot this graph. So what does it show? These maps highlight bright PL spots which represent individual entities. Okay, so this behavior, you can easily see the photoluminescence effect perpendicular to the axis of emitter is very less compared to this. So this is a very hallmark effect. It's a very common effect and it's known as antenna effect in individual carbon nanotubes, where emitted light is preferentially polarized across along the nanotube axis. Now we'll see we can plot the photoluminescence with cavity length. So as the cavity length increases, we can see the photoluminescence values have certain peaks, right? Specifically, okay, so actually the cavity was tuned over 3 different longitudinal mode orders. And for each mode order, the emission spectrum appears asymmetric due to the presence of higher order transverse electromagnetic modes. The cavity's line width is much narrower than the natural emission line width gamma of the entity. Because of this emission is directed only at the resonance wavelengths of the specific TEM modes. And the TEM modes are also shown here. It's using these square markers for different modes, where the modes are 0, 1, and 2, M plus N modes are 0, 1, and 2. The experimental data was fitted using 3 Lorentzian curves for each longitudinal mode order. And the higher mode orders greater than M plus N equals to, higher than this, were ignored since their contribution was negligible. Okay, so there are some key results which we can obtain. One of these is NTD emission wavelength is 1465 nanometer and the full width at half maximum is approx 28 nanometer. Okay, so finally we can plot photoluminescence with the mode order. I've already told the mode order. So the collected PL intensity of different nanotube defects was measured over 10 consecutive mode orders. The intensity values were normalized to the highest value and adjusted for variations in fiber coupling efficiency. So the efficiency of a fiber coupling depends on the mode waist, which varies with cavity length. Now this PL intensity increased sixfold when the cavity length was tuned to the lowest accessible longitudinal mode order. At this mode order, the mirror separation was around 2.5 micrometer, which is mainly limited by the 2 micrometer depth of the fiber mirror profile. The increase in intensity is due to a stronger light matter interaction coupling strength as the cavity length and the mode volume decrease. A smaller cavity mode volume enhances the coupling strength G, which in turn increases emission efficiency. So there is a mathematical relationship between this. And the low per cell enhancement regime, the nanotube defects population lifetime remains mostly unchanged by the cavity. The PL intensity is proportional to G square, and G square is inversely proportional to the cavity mode volume. That's why we are seeing this graph, and we have fitted this graph using 1 by x graph. It's an inverse relationship. So as we can see, it is fitted using this graph, V c to the power minus 1. Okay. So
Okay, so this meeting will end in 1 minute. So we will join again and continue from here. Okay, so welcome back. So Mainak has presented his results. बस अरे माइक बंद कर और तू अपना खोल
Hello, I'm audible.
Yes.
So, here we start from second order correlation. As we studies in our class that the relation between second order correlation and the light, whether it's bunching, coherent, or anti-bunching. So here we can see for bunching light, second order correlation should be greater than 1. For coherent light, it should be equal to 1. And for anti-bunching light, which is poorly quantum light, it should be 1, less than 1. So here we see in this experiment, we will see that the anti-bunching light, means second order correlation, we will found it will be less than 1. So here is the setup of HBT, Henry Brown twist setup. The setup is designed to measure photon correlation and determine whether the uh, NTD cavity system emits single photon or not. The setup description is the pulse laser excited the nanotube defects. Here we can see the pulse laser excites the nanotube defects. The emitted photon are directed into the fiber beam splitter, and then the two detectors at the output ports of the beam splitter record time correlation photon event. The collected data is used to compute the normalized second order autocorrelation HBT. We will see here the data. Here data of NTD1, which is light blue, and NTD3, which is dark blue. Here the result, if we read the result is shows the measurement of two different entities under condition of maximum cavity enhancement. And the presence of anti-bunching behavior confirm that single photons are being emitted key matrices at second order correlation of HBT at zero time difference. And the first NTD second order correlation at zero time delay is 0.31 plus minus 0.09. And second NTD is for correlation for second NTD is 0.09 plus minus 0.07. The value is much less than 1, indicates a strong tendency for a single photon emission. As we see above, as we see here, The second NTD exhibits even higher single photon purity than the first. Here we can see the second NTD is very less as compared to one. So it's showing a higher tendency towards the quantum light. And now we come to Hang-Wu Mandal interference experiment with an imbalance Mach Zehnder interferometer. If we talk little bit about Han-Wu Mandal interferometer, it is a interferometer that tell about uh, whether means how the interaction is quantum, means whether we are getting purely single photon or not. If the photon is more towards the quantization, then we will get a dip in the center of the uh, our plots. As we can see here, we getting dip. That's it is uh because its nature is more quantized. Um, Here the figure 4.1a, the indistinguishability of photon was measured using Hang-Un Mandal interferometer experiment with an imbalance Mach Zehnder interferometer setup. Experimental setup is a train of single pulse photon was split using a fiber beam splitter. The time delay delta was adjusted by varying the path difference delta t using a delay stretch. This allows two photon interference between consecutive emitted photon at the second beam splitter. A zero delay means the photons are separated by just one excitation pulse. The observation and results. The polarization of the interferometer's arms was adjusted using the fiber polarization controller. Detection events at the output port were analyzed to obtain HOM autocorrelation function G2 tau, second order correlation at tau time delay. Experiment were conducted for copolarize and cross-polarized configuration on NTD3. Here the experiment copolarize, it is shown by green light, and cross polarization is shown by orange line. And if we go further, the key finding, the copolarization case, there was reduction in the correlation at zero time delay, indicating quantum coherence to photon interference. Here there is dip at the t equal to 0. In this means that indistinguishable photon arrive at separate input port of a beam splitter tends to exist through the same output port, lowering correlation value. It is like a statement of HOM experiment in which when photons are more correlated, means G to G is towards 0, then we get output photon from a single port. So because of that, we get dip at the tau equal to 0. The photon indistinguishability visibility. The two photon interference visibility was measured as V equal to 0.51 plus minus 0.21. This account for factor like non-identical reflection and transmission coefficient of the beam splitter and the fine single photon purity of NTD3. Additional details and corrections are available and supplementary notes for which was explained by Dev. If we move further, here we see the graph of second order correlation of Mandal correlation and time delay. Here we see again the dip at t equal to 0, where green line represent a 0 picosecond time delay and 5 orange line represent the 5 picosecond time delay between two photons. Here we also see a dip at a 0, and the bars is the deviation in the mean value. Here Here we see the temporal PL, the decay of N-T1 dark green data and instrumental response. The orange line shows the result of by exponential decay model. Now, if we comes at the end of the paper, and the discussion is this study demonstrate a room temperature source of single photon in the telecom wavelength range. The photon emission efficiency and indistinguishability are significantly improved using incoherent NTD cavity coupling. This is a first experiment showing cavity enhanced indistinguishability for a quantum emitter that experience room temperature differentiation. The current two photon interference visibility is about 0.5, but it could be increased to nearly 1 by increasing cavity fineness to 35,000, which is possible with fiber-based cavity. Reducing the mode volume, which would be further boost emission efficiency by an order of magnitude. Even without these optimizations, this work is an important step towards room temperature quantum photonic device, which could be used for optical quantum computing, long distance quantum communication using optical quantum response. Thank you.
Okay, Sanjay, you can undo the screen share. Okay, so thank you very much for listening to our talk, and that was the paper that was been published in 2024. And thank you all for joining.